So I'll be talking about something which is sort of, the main motivation for speaking about something that I hardly work on is it satisfies some of the constraints on this meeting, the Indo-French part and the fact that it's classical and out of equilibrium. And also the fact that it has lovely pictures that one can look at. So large magnetic fields are common. You see them everywhere. So this is the magnetic field for on the scale of planets, Earth, that's solar wind. So this is sort of, the strength of these fields are sort of 1,000 times more from one to the other. Then, of course, in the lab, especially the French VKS experiments, which use liquid sodium to sort of look at this problem. So essentially, what is the dynamo effect? So I won't sort of go into the details, but just the point that we need to worry about for this talk. And the point is the following. So in a conducting fluid, if you, this blue line is essentially the fluid kinetic energy. So in some sort of developed turbulent state, you inject a small bit of magnetic energy, shown here by the red curve. And what you see is often in a finite time, the magnetic energy grows and it saturates. It need not saturate, it need not equal the same energy as the fluid energy, but the point is that there is a short time growth followed by some sort of saturation. And this you see in a vessel, so this is from a convective dynamo, which sort of mimics things which happens at the stellar scale. This is a turbulent dynamo, which is in some sort of collisionless plasma numerics. These are all sort of basically from astrophysical settings. And you see the same behavior. Here, for example, you see again, in some cases, the magnetic energy grow and saturate. In some cases, they decay, and we'll sort of look at this problem. And this is again, work from NESS, a couple of years ago, where again you see the same phenomena, and you sort of associate this growth of the magnetic energy with certain sort of changes which happens to the field lines of. So essentially, for me, an outsider to this field, the dynamo question is very simply what happens or how a tiny seed magnetic field grows and perhaps saturates in a conducting turbulent fluid. So that's essentially the question that we sort of would like to ask in some simple setting. And typically the answer to this kind of lies within the framework of what's known as MHD turbulence, where essentially you have coupled vector equations for the fluid field U and the magnetic field B, suitably written so that they have roughly the same dimensions, so you can sort of, make comparisons. And with often, I mean, this is not always the case, especially for astrophysical settings, incompressibility is not really the right setting, but for what follows, these might be useful. Typically, for people like us, it's useful to think about certain simplifications to this. So we know a lot, so maybe this should be what do I know. I know very little about this, but what I do know is certainly from several observations, experiments theory, and there's some sort of nice reviews that I've listed here, that certainly there are dynamos in 3 dimensions and there are no dynamos in 2 dimensions. The D equal to 2 no dynamo theorem is an old classic one. Now, to understand this question, typically simulations are tough, and I'm sort of trying to motivate this to show that it's a good idea to get away from simulations of those equations in this problem, and that's because in most realistic settings, you are really spanning a large sort of range of the fluid Reynolds number and the magnetic Reynolds number and the ratio thereof. I think most people sort of actually working on these problems would be interested in either this regime or this regime. Simulations and plasma experiments, such as the VKS, etc., are confined to this sort of bottom corner. And really, this to actually study things at those scales, you need you do simulations, but you do it not with the full MEG equations. All right. So a nice simplification to this work sort of comes what's known as a kinetic or a kinematic approach, and where you do the following. So you neglect the Navier-Stokes part of this equation. You're not interested in what's happening to the sort of the fluid field, and you say that I'll just worry about the induction equation for the B field, and you say I'm going to put things by hand for what the velocity field is. And this is not so uncommon in our business because you have things such as this passive scalar problem of Crichton, etc., where you play exactly the same game. So this is sort of, the most sort of well-known example of this, which has led to very interesting results. It's what's known as the Cousin-Seff model, where you essentially prescribe certain correlations on the U field. So it's like, it's something you prescribe by hand, and it's delta correlated in time, and you sort of take care to worry about this dijr, which is sitting in front of that correlation function. And all the information about the correlation, the compressibility, the roughness of the underlying flow, which you'll see starts to matter, sort of is all encoded here. And essentially two of the nice results, which sort of sets the stage for the work that I'm going to describe, is in the following. So this is a sort of paper from several years ago by Peter Horvey and Apronen, who sort of looked at the phase diagram of the dynamo within that Cousin-Seff model. So it's not a nonlinear model, it's not a turbulent model. It is, if you will, the analog of a Crichton passive scalar type model. And what they find is that you have so the x-axis is the dimension, and the y-axis essentially is the roughness or the regularity of the underlying flow. And what they find is that you have a dynamo phase the phase diagram which has these boundaries. And the interesting thing is, and perhaps that's useful for our world, is that in 3 dimensions you need very little regularity of the advecting flow to actually make things work. A more recent work, which is by Marco Drubadit and Dario Vincenzi, sort of extended the Peter Horvey work, and they included effects of compressibility. And this is quite surprising if any of you sort of are interested in this problem. That's because you'd normally expect that compressibility with its negative negative Lyapunov exponents, etc., would not self-sustain a magnetic field. But what largely analytical work, what these people showed is extend that phase diagram, but include compressibility. And as you make things more compressible, so closer to the astrophysical context, you again see a dynamo-no dynamo phase with these phase boundaries. Okay, so what I'm going to talk about in the next 15 minutes is the following, and it takes off from the work that I mentioned, and ask the following question, that if I look at the full nonlinear problem, the fully turbulent problem described by this set of MHD equations, do I have an analog of that phase diagram, which was done for the kinematic problem? So in particular, is there, so I'm borrowing terminology here a little bit, but so don't take the upper critical dimension part very seriously, unlike the talk on the random field Ising model. So is there a sort of dimensions between which you can have dynamo, and beyond on either side you don't get dynamo? So that's the question that we're interested in. So if I begin with this set of MHD equations, then the problem is that it's kind of impossible to actually numerically address this question. It's sort of useless. So what Sugan, Giorgio, and Dario, collaborators in this work, and I should sort of acknowledge the ongoing CEFIPRA project with Jason as the PI, sort of helped us understand what the solution to this problem is. So I'll just make a quick digression, because that's not something which is sort of spoken a lot of in the fluid turbulence community, is that looking at flows in arbitrary dimensions is done less frequently in our community, but it is done for very good reasons, which I'm sort of happy to discuss over lunch, let's say. And the early sort of study goes back to Fournier and Frisch, who sort of showed in this paper several decades ago that you do indeed have a critical dimension in these sort of problems, where the sort of famous inverse cascade and the role of condensates get limited as for dimensions greater than 2.06. And much later with Itamar and others, we were able to show that there is another critical dimension, that's dimension 4/3, where you essentially end up sort of getting turbulent but equilibrium solutions. And the nice thing was that this gave us a way to actually even do simulations of hydrodynamics in arbitrary dimensions, starting with some nice integer dimensions. All right, So let's go back to the question of how to build these theoretical models. So the starting point is that you can write down those same MHD equations I showed you in spectral space. It's a horrible mess of different projectors to satisfy incompressibility, etc. And then you sort of, what we are after, and this is really the point, even if we don't go through the derivation in any sense, is to actually start from here and come up with what these dots are all about. So to actually end up with an equation for the spectral energy, which will allow me to calculate the total energy, which will then allow me to study how that energy grows in time. Right? So that's really the program of this, and the details are messy, but you'll find them here. So I just wanted to also flash that these sort of closure ideas are also sort of used in several different areas, even in the recent past, and so it's kind of all right, because I'll give lots of caveats as I go along, but just to tell you that these closures work even when you compare with reasonable experiments and different sorts of problems in hydrodynamics. All right, so back to MHD, this is what we need to solve. So what we do is, so you can write down, for example, from the spectral equations, the equations for the second order correlators, and you immediately see, and I won't go through the hierarchy, but you immediately see that the second order evolution depends on third order. You go to third order, and then they start depending on the fourth order, and you sort of climb the ladder. So what one does is, and this was sort of this sort of couple of very nice papers by Steve Ozak and Pierre-Louis Soulem and Rose, which sort of tells you a little bit about how you make an approximation at the fourth order by assuming quasi-normality. So you essentially throw out, which in turbulence actually is the most interesting bit, throw out the non-Gaussian little bit that's left behind as you approximate the fourth order moments with combinations of second order moments, which I've sort of shown here. So you can replace X with whatever. And there'll be a whole bunch of these with UBB, etc., etc. So when you do that, then you sort of end up with something which is slightly easier to follow. Maybe this part is messy, but you end up seeing that you can close these equations on triads. So the nonlinear convolutions now have triadic interactions, which all sort of lie schematically within such triangles, and you know what that right-hand side is. The dots are now undotted, and you have some stuff. Sorry, Gautam, you had? Sorry.
If a perturbation parameter which allows you to do this?
Yes, in just basically here. So I just take the fourth order moment and I work out the cumulants, and there's a little bit remaining which I throw away, which I'll put back in.
So you can estimate. Yes. You can estimate those corrections.
Yeah, or you can make those corrections with certain eddy damping coefficients, which will help to factor in what you've thrown away. But maybe this level of detail we can discuss after the talk, right? Yeah. But you can estimate them. So which is why the approximation here is an important word. Okay, all right. So now we can go forward a little, and when we write this thing down, and you see all the small d's are the dimensional things, which has to do with the space dimension you're in, which has to do with the triangles of these triads. You essentially have good news and bad news. The good news is you're still conserving whatever you had to conserve in the original PDs. The bad news is that positive definiteness of energy is not guaranteed. So one has to do a little bit more at this stage, and the problem, as you'll see, will come from these operators theta hat. So the way one sort of goes through this again is you make further approximations, and by the way, U is really Sugan in this story, who was a PhD student of mine whose photo I flashed some time back. So what you do is you can saturate the third order moment. So Gautam, this is where roughly the approximity you're talking about, through certain eddy damping timescales, which you can then check roughly from simulations at say in 3D and 2D where you can do these stuff. And also you include a certain Markovization, which essentially says that your nth and n+1th correlators are relaxing kind of at the same way. So when you do all of that, you end up finally with an equation which has all the right-hand side terms. The dots have now been undotted, and you have all these terms with horrible-looking transfer integrals, which depends on all these triads. And in a real turbulent setting, when you have a large degree of freedom, the number of triads explode. So you have to sort of worry about all combinations of P plus Q equal to K, and we are in business. So let's sort of, in the 7 or 8 minutes that I have, but first let me sort of make a more physical meaning to these horrible sets of terms. So what you have here, and these make sense, that these terms, the word S, the letter S is for self, these allow us to transfer energy across wave numbers within the same fluid. All right? And this sort of conservation is guaranteed by construction in those sort of expansions that you saw. And you know that the integral of this over all wave modes has to go to 0. The C terms, which are the coupling terms, these sort of guarantee or this sort of tells you how energy is exchanged between the U and B field. And that's important, right? Because I will start with the seed magnetic field, so it has to get energy from somewhere, and we'll see where it gets its energy, gets its energy from the U field. And this, again, for conservation reasons, this will satisfy the following constraints. All right. So what we did, and we won because the proof of these equations was sketchy, but what one can do with our d-dimensional model is first, remember the Fourier-Frisch result that I told you about. You can set the magnetic energy to 0, and then you can look at existing results for d-dimensional fluid turbulence. That works. You can play the opposite game and seed it and see that dimension 2 and dimension 3, which is what you can realize in the lab or in nature, presumably, sort of those results also follow. So we are kind of happy with our stuff. So what's the strategy? So the strategy is the following. We will define the total energy, which is just the integral of these spectral correlators, and we are going to look at their ratio of the magnetic and fluid energy. Then we will begin with a zero magnetic field to begin with. We drive the fluid to steady state, so you end up getting the spectrum, depending on which dimension you are. It's either -3 or -5/3. And then at some T0, which we now set at 0, we are going to seed this flow with the magnetic, with a tiny magnetic perturbation. And we are going to see whether this ratio grows or decays. So what do we see? So that's really more or less the main part, and then I'll sort of heuristically explain, and we can use the blackboard for more detailed explanations. It's the following. So for some dimensions, if you look at this plot, and this is for Prandtl 1, REM1, the Reynolds numbers are quite high. I didn't mention what they are, but they're high compared to DNS, of course. And what you see is that for some dimensions, you see the magnetic energy grow. Eventually it will saturate if I waited long enough. Either it grows and then it dips, saturates, but the point is it saturates. And for certain dimensions, it actually goes down to 0, right? So you clearly see a dynamo, no dynamo phase as you, work with the system in different dimensions, which allows you to have the following sort of phase diagram. So this is dimension, this is time. One should really look at the top of this graph, and you see that there is a dimension which is 2.04, and there is a dimension which is around 6.5, between which you have a dynamo phase, and on either side you don't have dynamos. So is there a way to understand this? Probably not in the 4 minutes that I have, but I'll sort of try to sketch at least the argument. So the way to understand these critical dimensions is the following. You can sort of go back to the equations, the closure equations, and write down, at least for short times with certain suitable approximations, so you have the /approx there, the evolution of the magnetic energy. And what you then find is that for the phase where you do have dynamo, and you calculate these terms by hand to see what the net transfers are, you find that the predominant transfer on average is always from U to B. All right, and so the fluid is actually driving the magnetic field. And what you find that at short times you see a growth, whether it's exponential or not, we can discuss later. And at long times, you essentially, nonlinearity and the damping sort of saturates things. For dimensions which are in the no dynamo phase, what you find is that there is no effective forcing on the magnetic field, not surprisingly, but what you do find is that there is a preferential transfer from the B to U field at large scales and a transfer from U to B, which would act as the forcing to, stir up the magnetic field, but that happens only at small scales. And viscous damping is important there. So you try to feed energy at scales and viscosity eats it all up. And so essentially, in very short times, you get this behavior where everything dies. All right? And this is sort of best analyzed theoretically by looking at this effective transfer term. And because we know that if I take the limit of k going to infinity and look at the cumulative integral of this term, term by hand, or Sugan does, and then you certainly find that you have the following two scenarios, which sort of tells you a little bit about why you have this. All right, so I think I should, okay, so maybe just one plot of this. So for example, if you look at this term, you eventually see through analysis that the integral of this cumulative integral with k eventually goes negative as a function of k, and that means that this acts as the entire transfer is negative, it acts like a sink, and dynamo cannot be sustained. And you see that both for the dynamo and the no dynamo phase. The interesting thing is that there is a subtlety between why you don't have dynamos for large D, which is kind of slightly different from why you don't have it at small d, but that's for another day. And you can sort of look at the long time saturations. So let me conclude. Supriya will be happy, as promised. Let me conclude quickly. So what we did was we were able to sort of construct a d-dimensional, for what it's worth, a d-dimensional model to look at the problem of dynamos. And this model sort of gives us the existence of this dynamo-no dynamo phase boundary. And with this model, unlike simulations or experiments, I suppose, we can actually look at sort of span the space, this phase this diagram that I showed you at the beginning about where the galaxies are, where whatever solar wind is, etc. I don't even know the numbers very well, but you can actually show with this that for Prandtl very small, which is really you're talking about terrestrial experiments, the sort of the dimensions in which you can sustain dynamo get shrinks, and it really becomes kind of 3D. Whereas for very large Prandtl number, which is much more on the cosmological or sort of astrophysical scale, you sort of saturate to a finite upper dimension. And what do we want to do? What we perhaps want to do is, given that we have a closure model, we would like to play with the input velocity field, a bit like in the same spirit as the scalar problem or the Kazantsev model, and sort of includes various effects which seem to matter for people who actually study these problems and not use it as a nice game to play on differential equations and especially the idea of fields. Okay, so with that, I stop.
Thank you very much, Samriddhi.
Intuitive understanding and why this curve is non-monotonic. The first curve that you showed, psi star versus D.
The Peter Harvey work.
Yeah.
So I don't think that, they may have one, but I just followed the algebra. So it has to do with how the eigenvalues of that instability are.
No, but what I mean is that there is some kind of
Oh, but the sharpness is well understood. On the left side, the sharpness is well understood because as you approach d equal to 2, because of an added conservation law in the d equal to 2 problem. Okay, so so this part is well understood, of course. But when you go beyond d equal to 3, there is much more room to play with those conservation laws.
Other questions?
More than 3 dimensions, the magnetic field can be sort of a more complicated object, no? What exactly is meant by field in 5-7 dimensions, magnetic field?
What exactly is meant? how I would treat a fluid in higher dimensions. I probably don't have a good geometric or physical interpretation of that.
Okay.
But certainly, for example, if I think about turbulence, etc., I can think at low scales, because of fractality, etc., dimensions which are not exactly either the embedding dimension of 2 or 3. Now, whether I want to think about this problem in the same way, I'm not sure. So here the interest is not so much in the structure of the magnetic field, but the interest is in the structure of the triadic interactions which these nonlinear equations have.
Okay.
And so the geometries of those triads certainly make sense in arbitrary dimensions. And so the question really then becomes, somehow are those triads becoming more interesting if the spatial? So, but if you sort of push me to have a physical meaning to them, then I would have to take recourse to the fact that you can see in subspaces with an integer embedding dimension of d or 3. I'm not claiming that this does that, but you can think of dimensions which are.
Okay, thank you.
Other questions? Well, if not, let's thank Samriddhi and also all the speakers of this section.
Long live India and France friendship.